Hi kids, in this video we'll continue with class 9 physics, motion in one dimension, and we will discuss acceleration time graph. Now when you talk about acceleration time graph, the time is represented on x-axis, the horizontal axis represents your time, and the acceleration is represented on the y-axis. This is your acceleration. Now I've drawn both positive and negative. For acceleration it's positive, for retardation it's negative. Negative of acceleration is retardation. Now what can we calculate from acceleration time graph? We can calculate change in speed of a body in a given time interval, using acceleration time graph. And how do you calculate it? Just by finding area between the acceleration time sketch and x-axis or the time axis. If you find the area between them, that will give you the change in speed of a body in a given time interval, because we know what is acceleration. Acceleration is nothing but change in velocity by time, remember, or change in speed in a particular direction. That is your change in velocity. So acceleration multiplied by time gives you change in velocity. And how can we get this? By finding the area between the curve, the acceleration time curve, and x-axis. Now look at how many graphs we have in acceleration time. First one. Suppose the body is at rest, or you can say, or moving with uniform velocity. So how will the acceleration time graph look? Very easy. See, when the body is at rest, of course the acceleration has to be 0. Or if the body is moving with uniform velocity, then also there is no change in velocity. With one fixed velocity the body is moving, which means again the acceleration will be 0 because there is no change in velocity. In that scenario, the graph will be, just look over here, the x-axis only, which is the time axis. Because on this, if you take any point on time axis, the acceleration is 0. So this line on the x-axis represent your acceleration time graph when the body is at rest or moving with uniform velocity. This was case 1. Now take another case, case 2. When the velocity of the body in motion increases uniformly with time, which means the acceleration is constant. The body is in accelerated motion. Then what will be the nature of the graph? Then if you draw, just look over here, I'll draw it over here only. This is your time, which is in seconds, suppose. This is your acceleration. Then your graph will be a line parallel to the x-axis on the positive side of y-axis. because the negative side is your deceleration, retardation. So this will be a line parallel to the x-axis. This is your x-axis, this is your curve. The body is accelerated, in accelerated motion, in accelerated motion. Clear? Now look at the next case. Suppose the body, when the velocity of the body in motion decreases uniformly with time, which means the body is in retardation. What I'm saying? Just look over here. Case 3. Case 3, when the velocity of the body in motion decreases uniformly, with time, which means retardation is constant. Retardation is constant. Then what will be the nature of the graph? Then we'll get a line again parallel to x-axis but on the negative y-axis, which means we'll get a graph like this, because this represents your retardation. So when the body in motion, when the velocity of the body in motion decreases uniformly with time, then you get a line parallel to x-axis but on the negative side of the y-axis. That represents retardation. Am I clear? Now one more case is there. Case 4 I'll take. Case 4. When the velocity of the body changes in an irregular manner, which means the acceleration is variable, then you get a curve which is of any shape. You get a curve of any shape. The shape is not fixed, as in these 3 cases we know it will be parallel to x-axis on the positive side of y-axis. Over here when there was a retardation, I'll write positive y, negative y. Then it will be a line parallel to x-axis but on the negative side. So we know the shape. But for this case, when the velocity keeps on changing at certain time interval, then the acceleration is variable and you get a curve of any shape. I hope this is clear. 1, 2, 3, 4 cases. Now we'll look at the last portion of this chapter, motion under gravity, the curve related to that. The motion under gravity, very interesting. Just look over here. A body falling freely under gravity moves with an acceleration which is equal to 9.8 meter per second square. We roughly equal to 10 meter per second square. It's uniformly accelerated motion when the body falls freely under gravity. And if the body is moving vertically upward, then the retardation produced, then in that case the retardation, which is negative of acceleration, is 9.8 meter per second square. Roughly we take it as 10 meter per second square. This is uniformly retarded motion, you can say. Retarded motion. And from the acceleration time graph of a freely falling body under gravity, we can obtain 2 things. From acceleration time graph, we can obtain the velocity time graph, and from the velocity time graph we can obtain the displacement time graph. So we can draw both the graphs using acceleration time graph. Let us see how we do this. Now look, we know that suppose this is your time in second, this is your x-axis, and this is acceleration in meter per second square. This is your y-axis. I'm taking the case of acceleration when the body is falling. A body falling freely under gravity. Then we know it's an example of uniformly accelerated motion with acceleration equal to 10 meter per second square. Actually it is equal to 9.8. But we take it as suppose 10 meter per second square. Then of course, suppose this is 10, then we'll get a line parallel to x-axis. We'll get a line parallel to x-axis, isn't it? Suppose after 1 second, the acceleration will be 1 meter per second square. After 2 seconds also it will be same. After 3 seconds, after 4 seconds, after 5 seconds, like this. Suppose this is AB. So AB is your graph. The acceleration is constant, 10 meter per second square, uniformly accelerated. Now this was your acceleration time graph. Let us see how we can get the velocity time graph using this. Now look carefully what I'll do. I told you a little while ago that by finding the area we can get the velocity. Now look, for this region, you know, the area is length into breadth. It's a rectangular surface, isn't it? Figure. So velocity after 1 second, if you look carefully, length into breadth, that's 10 into 1, that's 10 meter per second. Velocity after 2 seconds, velocity after 2 seconds, again the area is length, which is 10, and breadth is now 2, so 10 into 2 is 20 meter per second, isn't it? Velocity after 3 seconds, again look over here, same, 10 into 3, that's 30 meter per second. Velocity after 4 seconds, 40 meter per second. Velocity after 5 seconds, will be again 5 into 10, that's 50 meter per second. Now using these data we can draw the velocity time graph. Look carefully. If you draw the velocity time graph, suppose this is time in second, this is velocity in meter per second. This is 1, 2, 3, 4, 5, and this is suppose 10, 20, 30, 40, 50. Then after 1 second it's 10, after 2 seconds it's 20, 30, then after 4 seconds it's 40, after 5 seconds it's 50. So what you are getting? See, for a body falling freely under gravity, from the acceleration time graph we got the velocity time graph, which is a straight line inclined at an angle to the time axis or the x-axis. So from acceleration time graph we got the velocity time graph of a body falling freely under gravity. Now from this we can get the displacement time graph. Look over here. How do you find the displacement from velocity? Area. We have done it earlier in my previous video. You can check the playlist. Now, displacement in 1 second. Displacement in 1 second. So this is the area. Half multiplied by base. Base is 1 and height is 10, which is 5 meter. Displacement in 2 seconds, if you look. Again, it's a triangle, right angle triangle. Half into base is 2 this time and height is 20. So that's 20 meter. Displacement in 3 seconds. Half into base into height. This time will be 30. So that's 15. 15 threes are 45 meter. Displacement in 4 seconds. Half into base into height. That's 80 meter. Isn't it? And one more I'll find. Displacement in 5 seconds. Half into base into height. That's 25. 25 into 5 is 125 meter. Now, if I draw the graph for this data, displacement time graph, just look over here. This is your, yes, done. This is your time and this is your displacement, which is represented by S. It's not speed, okay, it's displacement in meters, okay, in meters, time in second. 1 2 3 4 5 1 2 3 4 5 and your distance are 5 20 45 80 and 125. What I take, just look over here, this I take as 20 40 60 80, then this is your 100. I'll just rub this, I'll draw it over here. Just wait a second because there's less space. I'll just move this aside a little. Okay, we have enough space over here. Now, just look over here. This and this. Okay, this is 0, 1, 2, 3, 4, 5. This is suppose 20, 40, 60, 80, 100, 120. This is your displacement in meters. Okay, displacement, which is represented by S in meters. Now, after 1 it was 5, so this is 10, this is 5, somewhere over here. Displacement in 2 seconds will be 20. 20 is somewhere, if you draw properly, somewhere over here. Then you have 45. 45 is roughly I'm marking over here. Then you have 80 after 4 seconds. 80 is over here. So after 4 seconds is here, somewhere over here, isn't it? Look carefully. This is your 80. This was how much? At the end of 3 seconds it was 45. If you do in a graph paper, it will come very nicely. And after 5 seconds, 125. 125 will be over here. Somewhere over here. Isn't it? Somewhere over here. Now if you join the line, just look over here. If I'm joining the line, I'm getting a curve. So this represents the displacement time graph for a body falling freely under gravity. It's a curved line. Now a very interesting thing we notice from here. This was your time in second, and this was your displacement in meter. I'll rub this part, okay? Now look carefully. From this graph, we get one thing, that the displacement is directly proportional to the square of the time. The displacement, the body falling freely under gravity, is directly proportional to the square of the time. If I write the data, just look over here. If I write the data, if I write t square, and this is displacement, 1 square is 1, displacement is what? 5. 2 square is 4, displacement is what? 20. 3 square is 9, displacement is what? 45. Then 4 square is 16, and displacement is what? 80. 5 square is 25, and your displacement is what? Displacement is 125. We'll try to draw the graph for this. Just look, very interesting graph. Just look carefully. This is displacement, okay? This is your t square. 0, 5, 10, 15, 20, 25. This is your displacement. Suppose this is 20, 40, 60, 80, 100 and 120. Now we'll plot the point. See, when t square was 1, displacement was 5. So 1 must be over here, 5 somewhere over here. T square is 4, which means over here. Your S is 20 over here. T square is 9 over here. Your S square is 45. 45 is somewhere over here, isn't it? Then your T square is 16. 16 is over here. And your S is what? 80. 80 is over here. So somewhere over here. Yes. See? 16. This is 80. When your T square is 25, your S is 125. This was 120, so 125 somewhere over here. So there's somewhere over here we are getting. Okay? If you join these, you get a straight line inclined to the x-axis at a certain angle. Isn't this is the S displacement t square graph for a body falling freely under gravity? Now, if you find the slope of this, very interesting fact, just look over here. I take this point, which was 4, and this was 16. So, when t square was 4, S was 20. When t square was 16, it is 80. So what is slope? Change in y coordinate, which is 80 minus 20, by change in x coordinate, which is 16 minus 4. That's 12. This is what? 60 by 12, that's 5. This was in meter. Second square, which is equal to half of g. G by 2 is this only. So the slope in this case is nothing but g by 2, which means we can get the value of g. If you double the slope of S t square graph, then you get the value of g, because g will be clearly twice of slope in case of S t-square graph. Am I clear? Keep it till here in this video. In the next video, we'll look at the numericals from this chapter. If you like this video, do subscribe. Okay? Till then, take care and be safe.